We have two speakers today. Gary Gilmore, who will speak first, is a service forester with the Pennsylvania Bureau of Forestry in Jefferson and Armstrong counties. His personal interest in charcoal has led him to experiment with this product in a number of applications, all with an eye to small-scale systems capable of being sustained easily. He uses firewood from his tree farm for heat, is developing a wood gasification system to run engines, and is incorporating biochar on his own land as an amendment to increase soil health. He will share some of these experiences with us today, and he's on the lineup first. David Laird will speak second, expanding on principles of the small-scale approach Gary will introduce. David received his PhD in soil science from Iowa State University in 1987 before working with the USDA ARS Soil and Water Management Unit, National Soil Tilth Laboratory, and now is a professor in the Department of Agronomy at Iowa State University. David has served several editorial and management positions in the societies and journals of the Soil Science Society of America and the Clay Minerals Society, and is a fellow in both the American Society of Agronomy and the Soil Science Society of America. He has co-authored 89 Reverie Journal articles and 13 book chapters, which have been widely cited. Among other research interests, David explores the use of biochar co-products of biomass pyrolysis as a soil amendment and its impact on soil quality, nutrient leaching, and carbon sequestration, leading him to speaking with us today. So maybe the best thing to do is that while we sort out this audio issue, David, would you mind going first? And then maybe we can work with Gary to make sure that we're able to hear him for the second part of the presentation. So the only thing this will change is that first we'll hear about larger scale applications, and then we'll move into smaller scale. David, is that all right with you?
Can you hear me here?
Yes, I can hear you fine, David.
I'm happy to go forward if you want to put up my notes.
I'll do that.
Well, thank you, and appreciate Sarah putting all this together, and look forward to hearing Gary here in a few moments. I'm David Laird. I work with Iowa State University. I'm a professor in the Department of Agronomy. Most of my work has been in the area of soil science, the interaction of soils and biochar. I've worked in soil chemistry, soil mineralogy, quite a number of areas. Today, however, I'm going to talk primarily about the pathway to commercialization. Now, this is probably not my area of expertise, but it's an area where I keep getting lots of questions because there's a lot of people who are interested in finding out what the pathway to commercialization is. And so I'm going to offer you my perspective, and that's all it is a perspective. But it's based on my contact with the industry and with various producers. So, to begin with, pyrolysis is a thermochemical platform for transforming biomass, such as corn stover, into combustible gas known as syngas, a liquid known as bio-oil, and a solid co-product called char. Both the syngas and the bio-oil are combustible and can be sold as energy products. The syngas is typically used, however, to provide heat and power for running the pyrolysis system. The vision here is, and the problem is, how do we pay for the biochar? And one approach, or one hope, is that by co-generating energy products and char at the same time, we can make the biochar industry more economic. So There are a number of industries, a number of companies that are beginning to produce large-scale biochar. Probably the most widely known is Cool Planet, and they are in process of constructing a 10 million gallon per year facility down in Louisiana. But there are several other companies that are starting to work on production of biochar at a large scale. Another example is renewable forest energy in Pagosa Springs, Colorado. And they're in a unique position because they're surrounded by national forest lands. They have a contract with the Forest Service to harvest bark beetle killed trees, and the Forest Service wants them to get those trees out of the forest so they don't burn. And so basically their feedstock is supplied to them essentially free. And their vision is to build a gasifier and to produce electricity and biochar as a co-product. And I believe they will be hopefully up and running within maybe a year, year and a half. The rest of the biochar industry, however, is at a very small scale. The IBI 2013 survey reported just 827 tons of biochar being produced with an average selling price of $2,480 per ton, which is very large price, but it's because we were selling in 50-pound bags or mixed composts and this sort of thing. So it's really at this point very much a niche market. Some of the potential applications that are starting to emerge. One of them is as a component of potting soil, greenhouse potting soil mixtures, soilless media, and these are actually some greenhouse plants that were all grown in mixed biochar, sphagnum peat moss, soilless media. And so this is a potential market, both because the aggregate, which has typically been used, such as vermiculite, is expensive and getting rare. Perlite is another possible aggregate that biochar would replace, and it is a bit hazardous because of the dust issue associated with it, a silica-rich dust. So biochar has been shown to be effective and has some other advantages in a greenhouse. Namely, it provides a liming agent which counteracts the acidity of sphagnum peat moss. So it's been shown to be actually quite effective in this application. This comes courtesy of Tom Miles, his suggestion that biochar could function in a number of urban settings as urban water retention structures, for roof totes designed to capture runoff from roofs, and particularly where you have galvanized roofs, maybe remove the zinc from that water. Another application, a potential application that could be quite large, would be in mineland reclamation. This is a project from Biochar Solutions in which they had some mine tailings that had gone 60 years without revegetation, and after the biochar was added, they were able to easily establish the vegetation, and this is because the biochar helps in the retention of nutrient and water, which mine tailings are notoriously lacking. Another application which is growing, and this slide comes courtesy of Lassiter and Easton, is use of biochar as a component or as a mixture in denitrifying bioreactors. And this test, by the way, is going on in the Chesapeake Bay watershed area, where you have high levels of nutrient runoff causing hypoxic conditions and outbreaks of toxic organisms such as Listeria in the Chesapeake Bay, and so there's a very serious environmental challenge there. And the vision here is to essentially put a curtain, so dig a trench, fill it up with a mixture of wood chips and or biochar, such that water running off from the landscape has to pass through this curtain before it gets to the stream. And if we look at some of the data here, this is this is a mixture then of wood chips and biochar being prepared for such a reactor. And if we look at the data, on the left, you can see an example showing the nitrate concentrations, both the peak or maximum and then the average concentration in the groundwater upgrade from the bioreactor. Surface water or runoff has relatively low concentrations of nitrates. Preparing a bioreactor with just wood chips was highly effective at removing the nitrates, and it was also effective when you had a mixed biochar wood chip reactor. On the left, on the right here, we're showing the phosphorus runoff in, again, the maximum and the groundwater levels. Surface runoff, phosphorus was a little bit higher. Going through the wood chip bioreactor, the phosphorus was not abated at all. It came right through. However, when we had the biochar plus wood chip reactor, we were able to remove the phosphorus from the system. And phosphorus is often one of the limiting nutrients for eutrophication. Another potential application of biochar is in high-value horticultural crops. Here we see an image of California strawberry producers. USDA Economic Research Service estimates that it costs on average in California about $45,900 per acre to produce a crop of strawberries. So this is a very high-value crop. And a few $1,000s for biochar per acre is a minimal investment. And the key potential advantage in this kind of a scenario is water. In 2014, this year, there were some 430,000 acres of essentially prime agricultural land in California that were left fallow basically due to a lack of irrigation water. And you can see in this aerial photograph that the brown fields are essentially those that were taken out of production because there was not enough water. And the opportunity here then is if the biochar could improve water use efficiency, then it would spread the water a little farther and allow some of this land to come back in production, or at least allow the water to be used for other purposes. Some of our data, shown here in the upper left, is volumetric soil volumetric water content as a function of the amount of biochar applied in tons per acre. This was measured on a summer afternoon, and we see here a very strong correlation and almost a 35% increase in the soil water content that was measured on that particular day. Now down here in the lower right, you see water content that has again been measured, but now over a much longer period of time. We've been continuously monitoring water. This is in the surface soil, and so the light green are the biochar treated plots, and these are averages of 4 plots, and the red represents the control that doesn't have biochar. And you'll notice now that in the June-July era, part of the year of 2013, we had significantly higher water content in the biochar amended plots than the control. Then as the summer dried out, the water content of the biochar treated plots was lower. Now the difference between here and here, the high and the low, represents plant available water. So the biochar-meted plots in this example provided actually more water for the growing crop. During the later fall, we had some additional precipitation, and the biochar plots accumulated more water. During the winter season, basically they were the same, and then coming into the spring season of 2014, we are again showing increased water content of the biochar treated plots. We've yet to provide clear evidence that this increased water use efficiency will result in higher yields, but it is consistent with the ability of char to help retain water. And so we have a fairly good hypothesis that in more arid environments, such as California, char will be able to increase water use efficiency in high-value horticultural crops. Another potential example involves char mitigating soil physical problems. Along the I-95 corridor in southeastern U.S., there is a zone of hard-setting soils. These soils have a E-horizon, which basically turns to a brick when it dries out, and it can be so hard that plant roots are unable to penetrate it, and as a result, it can have very poor crop performance. The Australians have been interested have large areas of these hard-setting soils and have recently been studying the impact of char on the hard-setting soils. And so here you can see the difference between a char-amended and a control soil. And their data suggests that crop yield does respond to nitrogen when char is applied, but does not respond very well in the absence of char. And so they're showing actually quite substantial yield improvements in these char-amended hard-setting soils. And over here, physical measurements, tensile strength, shows again that char amendment is able to help mitigate this very serious physical problem that occurs in many soils. So this is data from the USDA looking at Florence County, South Carolina, in the middle of this hard-setting soils. These are corn yields, and you can see the average since 1980 has been only about 80 bushels per acre, and there are a number of years in here where the yields have actually been abysmal. Compare that with Iowa, where the average yield is over 180 bushels per acre. This is very poorly productive land. Yet, when we look at the rainfall pattern in Florence, South Carolina, we see that they're getting 42 inches of rain a year, and the July-August period is actually when they receive the most rainfall. So the problem here is not that simply too little rain. The problem is related to these hard-setting soils, and we believe that, again, biochar could mitigate some of these problems. We take an aerial photographic view of this area. We see a mosaic of southern soft pines, loblolly and other pines, and crop fields. So here's the forest, here's the fields. A survey of realtors in Florence County, South Carolina, showed an average agricultural land price of only $2,600 per acre. If we could mitigate these physical problems that are hurting the soils and the productivity of the soils in this region, we could probably double or triple that land value, and that could be attributed, that difference could be attributed to the biochar treatments. So it's potentially significant value in the biochar under this scenario. In the Midwest, I come from Iowa, we see the emergence of cellulosic bioenergy. This is DuPont's cellulosic ethanol plant that's being built near Nevada, Iowa. There are a couple others out, Poet up in Emmetsburg and Abengosa are also coming online now, producing ethanol from corn stover. And so this is now a common image in Iowa to see large bales of corn stover being harvested as feedstock for these cellulosic ethanol plants. First thing I want to know as a soil scientist is what's going to happen to the soil if we take all this residue off. And there have been a number of studies, several of which we've been involved with, that show long-term harvesting of residue results in loss of soil organic matter, a loss of nutrient, loss of water holding capacity, long-term degradation of soil quality, and ultimately productivity. And so the challenge then, if we're going to harvest biomass for bioenergy production, is how do we change our management systems to make them more sustainable. And so one of the areas of research that I've been involved with extensively the last decade or so has been testing the hypothesis that biochar amendments could help mitigate these long-term negative effects of residue harvesting. Now I'm going to show you some data here, and this is a bit complicated. This is a yield of bushel in corn, yield of corn in bushels per acre, and down on the, I'm jumping around here. Okay, down here we have 0, 50, or 90% above ground residue removal, and this is cumulative data for 5 years, so we have averaged the results from 2008 through 2012. So first of all, we'll look at the effect of biochar when we are not removing any residue. So this is continuous corn production, and now we're seeing a 12-13 bushel per acre yield increase with our highest char treatment of 8.2 tons per acre. The 4.4 didn't seem to have much of an effect. However, you'll also note that when we remove 50 or 90% of the residue, we are seeing an even bigger yield increase. This may sound a bit contradictory to what I was saying just a moment ago, that long-term harvesting of stover degrades soil quality, but it's not. That still stands. This is 5 years is relatively short time period, not enough time period to show the degradation of the soil quality. Instead, what's happening here is that the residue is toxic. As the residue from the previous year decomposes, it's releasing certain types of compounds, phenolic compounds, that are autotoxic or basically poisonous to the emerging corn crop. And this is why we see in continuous corn, the blue is our continuous corn control, much lower yields than when we remove part of that residue. So we've got an interesting opportunity here. Farmer can remove some of that residue, get paid by the cellulosic ethanol plant for the residue, and see a boost in corn yields. So it's a win-win for the farmer in the short term, but in the long term, over a 20-30 year period, it will result in degradation of soil quality. So it's a bit of a dangerous situation in which we are putting an economic incentive to remove that in the residue in the short term at the risk of long-term loss of productivity and soil quality and of carbon. Now, when we've added biochar to these plots where we've been removing the residue, we are not seeing, at least not as of yet, seeing a yield response. I think eventually we will, but that's still perhaps many years in the future as the effects of soil quality become more apparent. The reason we see a response when we don't remove any residue is because the biochar is absorbing those toxic compounds, those phenolic compounds that are poisoning the next year's crop. So that's why we see the response here, but we do not see the response when we remove 50 or 90% of the residue. Looking at this from an economic perspective, we have two scenarios. In the first scenario, we're considering the price of corn being $4 or $5 per bushel, and we assume that we're seeing about a 12 bushel per acre yield increase in a continuous corn system. And we come to the conclusion, based on this analysis, that the value of the biochar to the farmer is only worth $50 to $60 per ton. Now, to make this analysis, we assume that the farmer took out a 20-year loan with a 5% annual interest rate, and we asked the question, how much could the farmer afford to pay in order to meet the payments on that loan? In the second scenario, we still keep the $4 and $5 bushel per acre corn price, but we now consider that the farmer is moving 3 tons of stover per acre per year, and as a result of that stover removal and the biochar amendments, the farmer is now getting almost a 23 bushel per acre yield increase and getting paid by the ethanol plant for the stover that's being harvested. With this scenario, we are able to assign a value to the biochar of $250 to $300 per ton. And this starts getting into an economically viable range. So the key here is that the char's role is not so much to enhance yield as it is to enhance the sustainability of the stover harvesting. And finally, I've been working with Mark Wright here at Iowa State University to try and develop techno-economic, a simple first order or zero order techno-economic analysis of what the biochar market might look like. Given the current situation, this is all pretty much hypothetical. Basically, we've looked at a number of potential applications and tried to estimate the value that the farmer or industry could afford to pay for the biochar, and so this is the result you're seeing here. On the left, we have the market size, and you'll note this is a log scale. So 10 to the 6th is 1 million tons. 10 to the 8th would be 100 million tons of biochar per year. And the price down here starting at about $1,000 a ton, and then when we get much over 1 million tons per year, the price starts to collapse down to lower value applications. So this is, again, hypothetical at this point in time, but we think this is our best guess as to what the size, value, market of the biochar industry might look like. So bringing this presentation to a conclusion, first of all, I'll say that a small-scale niche biochar industry exists today, and these are primarily selling biochar to backyard gardeners, some horticultural applications, and maybe a few land reclamation projects. Secondly, we do see an opportunity for expansion of the biochar industry in the future, particularly areas of land reclamation, both mine land and urban brownfield, stormwater retention, a greenhouse soilless potting media, number of applications potentially in the poultry, swine, and cattle feed industry. This is actually getting a lot of attention in Europe right now. Reduction of nutrient losses from confined animal feeding operations, both capturing and potentially recycling nutrients. See opportunities for reduction of nutrient losses. These are environmental opportunities through the use of anaerobic bioreactors. We see a number of high-value horticultural crops improving nutrient and or water use efficiency. And we also see a potential for, if we see growth in the bioenergy industry, for biochar to play a key role in sustainability of biomass harvesting and improving physical properties of hard-setting soils. And I end with a question mark because I think there's lots of other potential applications out there. But again, we're not there yet, but my guess is that there is the opportunity at this point for growth in this industry. So with that, I'll turn it back to you, Sarah, and hopefully we'll be able to hear what Gary has to say.
Thank you very much, David. We have some very good questions come in. I think first we'll try to see if Gary's back with us. Gary, are you on?
Yes, can you hear me?
Excellent, yeah.
Can you hear me?
Yes, we can.
Can you hear me?
We can hear you, Gary. Can you hear us?
Okay, good.
So, at this point, let me bring up your presentation, and some of these questions I think maybe will be answered by, but if they're not, then we'll get to them all at the end so that you and David can answer them together.
Okay, let me get going here. Apologize for the speaker. I don't know what happened, but anyhow, just to build on what David says, charcoal is an ancient fuel. It's wonderful. Most of the people in the world today are actually cooking on wood or biomass. And charcoal is the only product on the face of this earth that brought us out of the Stone Age and into the Iron Age. So without charcoal, folks, we would actually be living in the Stone Age. Now, not only as a fuel, but charcoal has this wonderful ability for filtering, and it's been used in gas masks, and it's also been used in water. A picture here from the 1800s of a water filter before they even knew about bacteria. They knew that charcoal could sweeten stale water. So it has these amazing properties and pretty ancient. Now, let me make this clear. When charcoal is mentioned, it's typically used in the context of a fuel. But when we use it in the soil, as David just mentioned, the term gets turned to biochar. And what it means is just basically charcoal, which is committed to the soil. And due to constraints on time, I'm just going to keep moving here along. But when you look at a piece of biomass, this happens to be a piece of pine. Look at it under a magnifying glass, and you see this tremendous amount of tubular structure, which is made up of cellulose glued together with lignin. These are the tubes that transport the water from the. See if I have my pointers here. Can you guys see my pointer? Okay. These are used to transport the water from the root system up into the leaves of the plant. And there is where carbon dioxide interacts through the photons of the sunlight under photosynthesis to sequester carbon in the plant material. This is a piece of oak. Notice it's much denser, but it has a tremendous vascular system in it. Now, when you make charcoal, basically taking the hydrogen and the oxygen that are part of the cellulose and lignin molecules, and you're removing them, baking them off, and leaving carbon behind. And this carbon is what charcoal is. But the structure of the green plant that is evident in this picture is still intact once the charcoal is made. The structure isn't really, it's degraded a little bit, but still you have a tremendous vascular network throughout the plant material, which is evident after you making the charcoal. Now, charcoal has some unique properties. It does not decompose. Nothing eats it. No fungi, no bacteria. The only thing that really decomposes it is fire. It doesn't compress or stick together. It doesn't compact under pressure. It has a high anion cation exchange capability, which is extremely important in nitrate retention and phosphorus retention and ammonia retention. It has this huge surface area. It acts like a sponge. Now, this is a picture of some TERRA PRETA, dark earth found down in the Amazon River Basin. Basically, it's a man-made soil. They use charcoal, which carried the nutrients from the village onto their fields where they then farmed it. Because typical jungle soil is high in clay and very nutrient poor. So the Indians in the Amazon actually engineered a soil, and over a period of thousands of years, it got pretty deep. And it's still productive today, even though it hasn't been farmed. Now, folks, I'm kind of focusing on charcoal in the soil because I see that as a huge benefit of charcoal. And this is just a very familiar diagram of the soil food web of healthy soil, where we have the inputs from the sun, growing plants, producing organic matter, and then you have all these different levels of fungi and bacteria, and nematodes, and arthropods, protozoas, all feeding on something, all creating waste, all recycling it. It's going into a system, and it goes around and around. And on the far right, of course, would be us humans, benefiting from this digestive system, which healthy soil is a digestive system. Now, charcoal in this system can act like a battery, and it will help hold the nutrients that are created in this system and make it available for the plants. Right now, it's December in Pennsylvania. Any nitrogen that fell to the ground from the decaying plant material may get converted into nitrates, and then over the winter, rainfall and such, would leach that nitrate out of the soil. Charcoal can hold that nitrate in the matrix of the charcoal and keep it on site so that next year when the plants start to grow, they can actually mine the nitrates out of the matrix of the charcoal and use it for growth next year. So when we add charcoal to soil, we're affecting the physical, chemical, and some of the biological aspects of soil. So when we look at soil, some of the physical properties are, the texture. Well, adding charcoal to soil changes the density. It reduces the soil density because charcoal is so lightweight. By reducing density, you also increase the tilth of the soil. This increases porosity. You saw what a sponge-like material that looked like. So when you increase porosity, you increase the aeration, the gas exchange from the atmosphere to the root system and the root system to the atmosphere. The porosity allows water to easily infiltrate charcoal-enhanced soils. And because of the deep pore space in charcoal, you have a lot of water retention. This is just a very simple experiment I did. I filled this quart jar with charcoal. The other quart jar was filled with water. I took the water and poured it into the charcoal. It took about 2 days for the charcoal to absorb all the water. But what you see in the bottom of the jar on the right-hand side is the water I could not put into the charcoal-filled jar. And this represents the actual physical space taken up by the charcoal. The rest is pore space taken up by water. Now, just think of the implications this would have for retaining water in droughty soils or sandy soils. Think about using this as a subbase to absorb stormwater runoff. So some of this water could then be poured back, but the charcoal pores will hold a tremendous amount of water. Okay, chemical properties. Well, charcoal has a temporary, it's somewhat alkaline. It has a pH around 8.5 to 9, depends on how you make it and what you make it out of. But in our Pennsylvania soils, which are very acidic, this is actually a nice benefit. But one of the big benefits is this cation-anion exchange capability. Charcoal holds ammonia, it holds nitrates, it can hold calcium and phosphorus. As David already mentioned, it can be used as a way to mitigate the movement of these materials off of a farm field and keep them on the farm. It also has a large surface area that can absorb organic and ionic compounds. As far as biological, not too much. Depending on how the charcoal is made, there may be some food value in the charcoal, not much. It may also provide a place for microflora, fauna to hang out, like, fungi may hang out in some of the pores of the charcoal and then can reintroduce into the soil. But not a lot of biological properties. So when you add charcoal to the soil, you have these benefits. Methane emissions, should you have an anaerobic soil condition, it reduces it. It reduces the nitrous oxides coming off the soil. And because of that, the nitrogen stays in the charcoal, therefore you don't need as much nitrogen fertilizer. Reduces the leaching of nutrients. It stores carbon in a long-term stable sink. In other words, charcoal committed to the soil is going to be there for centuries. It doesn't decompose. It reduces soil acidity. This cation-anion exchange capability we already mentioned, and a place for fungi to kind of seems to help the particular mycorrhizal fungi. Now, before you add charcoal to the soil, there's some things you really should do. One of them is prime it. In other words, charcoal is looking to absorb stuff. And if you can soak it in some sort of nutrient-rich material, whether it be compost, poultry manure, swine manure, cattle, horses, whatever, even some nitrogen-rich material, this primes it so that when it goes into the soil, it already satiated it, and then it can give up its nutrients to the plants. It should be small. I like to say size of a corn kernel or down to dust. And finally, it should be damp. Charcoal is very lightweight. When it is put out, it can easily be blown around, so therefore you need to dampen it to give it stability so it can then be incorporated in the soil. Now, I've been using charcoal in my garden for the past 5 years, but I have never quantified anything. Last year, I set up this little bean experiment. These 6 pots are filled with varying degrees of charcoal, and on the left is my control. It's just plain old topsoil, and in the pot next to it, I put 5% by volume of charcoal in with the topsoil. The next pot, I doubled the amount of charcoal and put in 10%, and then doubled and doubled. And the last pot has 80% charcoal and 20% topsoil. Put them on my wall, just let them grow for the year. So at the end of the year, I gathered the beans, I dried them, and this is the weight in grams from each pot, which had 4 bean plants in it. So you see in the control, I got 1 gram of beans, and then just by adding 5% charcoal, I tripled. 3 times. At least 3 times the amount of beans. and so forth. Now what surprised me was the 80% char even grew a bean. I was thinking almost pure charcoal. I did not prime this, so there are no nutrients in it. But those beans survived and put out 0.6 of a gram. Okay, this year I did the same experiment, and my hypothesis was that the pot with the 80% charcoal would start doing better as that charcoal became charged with basically nutrients that would fall from the air in the form of either rain or snowfall, and also the plant material that would have died and fallen back into the charcoal. So here are the results from this year, just about 2 months ago, and you can see now the 2014 information is in the yellow, and you can see where the control actually doubled from last year. We had a lot of rain this year, so there was no restrictions there. But even though it doubled, it is still 1/3 less than what was growing in the 5% pot. And then you notice the 80% pot, and it's doing much, much better. So does charcoal help in the growth of these beans in that type of soil? And I say unequivocally yes. And this experiment will be done again this year. Now I gave some biochar to a friend of mine who put in these experimental plots, and you see on the left is just plain old garden soil, and on the right she put in 5% by volume of charcoal. You see by June 9th there's a difference. June 25th even more, and by June 19th it made quite a bit of difference. And then she harvested these crops, and these pictures are self-explanatory. On the left is the control, and on the right is the plot amended with 5% charcoal. And in every case, not only were there more vegetables, but they also were larger. Kind of more impressive than I would have expected. I'm still offering that to you as proof that biochar does have some benefits. Okay, charcoal can absorb up to 5 times its own weight in water. Tremendously porous, just like a sponge. It absorbs organic molecules, urea, proteins and such. It absorbs mineral compounds. We already mentioned about ammonias and nitrates. So here's my little mini pony standing in a stall, and underneath his feet is a bunch of charcoal I just threw in. I started doing this about 4 years ago, and I let the pony then grind it into the manure. He urinates on it, defecates on it, then this gets put on the garden. Well, soon after applying this charcoal, I noticed the odor in the barn went down dramatically. And then I noticed the fly problem almost disappeared. And to this day, we have very, very few flies as long as I'm adding charcoal to the manure. Now, think about using manure or charcoal in a concentrated farm animal operation where you have tremendous amounts of odor. I'm thinking of swine, I'm thinking of poultry, where you have fly issues. Could charcoal be used to mitigate these issues? And I think unequivocally, yes, it can be. And we need to start looking at that here in the future. So charcoal has these other uses. It's used as a water filter, trapping nutrients and bacteria that's coming through the water. I use charcoal in my vegetable storage operation. The charcoal is laid down, and the potatoes and the apples put on top, and it absorbs ethylenes and absorbs any odors from any vegetables that are rotting. Helps preserve the others. We already mentioned odor control, waste recycling. I'll show you in a minute. What about using charcoal for green roofs? It's a lightweight material. It holds a lot of water. And then that water is available much longer than if your substrate was made out of rock. And it's made from organic material. And it's a form of carbon that is literally sequestered for centuries, if not millennia. And then if you're tired of your green roof, put it out on a farm field where the charcoal can then be used by plants in that area. What about using charcoal for hydroponic substrates. Instead of using stone or expanded clay pellets, use something that's grown instead of mined. These are all things we need to look at. I'm also experimenting with waterless sanitation. Here is my experiment with a charcoal commode, where I'm using charcoal to basically capture the odors and the nutrients. These are then later composted, but it's a waterless system and no odor as long as the charcoal is used. Okay, moving on real quickly. How do I make charcoal? The traditional way was stacking wood up, covering it with leaves and grass, and then lighting it from the top and tending it 24/7 for about 3 weeks or more. Well, other people are now using metal containers like steel drums. And if done properly, you don't have smoke. This is a very smoky method this person is using, and it's totally unacceptable. We cannot afford to smoke out our neighbors. And there are ways of doing this without creating a lot of smoke. And one of them is to take your wood, and if you're using wood, you can use grasses also, but to dry it. Because dry wood, less moisture, the more charcoal, and the higher your yield will be. So here's some aspen I cut that's dried out over the summer and is ready to be made into charcoal. I stack, in this case I'm using wood, so I stack it in a steel drum. At the bottom of this drum are air inlets. You'll see those in a few minutes. It's filled with wood, and then a fire is lit at the top of the drum. At the bottom of the drum you can probably see those little slits, which are the air inlets. Now, the key to smokeless charcoal making is to use an afterburner in this style of charcoal making. And the afterburner is nothing more than another drum without a top or bottom. It just acts like a large chimney. So here I am. I just lit the fire at 8:25 in the morning, and I step back and you can see the smoke out of the top of the barrel. Within 5 minutes, that smoke has dissipated and the fire is starting to burn. Now, within an hour, I took off the afterburner and I looked in. The fire's doing really well. It's starting to burn down toward the air. Fire always moves toward the oxygen. So I then put the afterburner back on and came back an hour later, checked it again. Poked around with a stick to see if there are any unburned pieces there. Put the afterburner back on. It takes maybe 15, 30 seconds to do this. So here the fire has finally come down to the air inlets, and it's time to shut it down. That just simply involves taking some soil, dirt, packing around the holes, and then letting it cool off. Okay, I'm missing some slides here. Okay. Sarah, is that? There are quite a few more slides. Okay. There we go. Anyway, you put a lid on top of the barrel and basically let it cool down. Yeah, there we are. The lid off the following day. The charcoal can be screened, and it can be simple as an incline with a screen where the fines and the ashes are dropped out, or you can be a little more sophisticated. This is a rotary screen with big chunks of charcoal fall into the bucket. The finer pieces can either be used as biochar or for other products. And then this is a furnace I built in my shop to capture the heat when I make charcoal. And basically, it's a water jacket on top of a steel drum in which a fire is burning. And in front of this furnace is a box of woody material which I'm going to be using for the for my charcoal. And here the drum is. It's rolled out from underneath. You can see inside the large 55-gallon drum is a smaller one where the fire is located. The fire, again, is lit at the top. The drum is then slid underneath the heat exchanger. About 3 hours later, pull the drum back out. I have this charcoal, which can then be put into another drum and cooled down. And this then allows to extract heat from the wood and then also to get charcoal from it. The charcoal has energy in it. There's a gallon of gasoline here. Behind it is 12 pounds of charcoal. They have the same energy equivalent. So I use charcoal and gasify it to make carbon monoxide to run, in this case, my Gravely tractor. In the milk can on top it's full of charcoal, and the air coming in, you can see the bright glow of the fire is creating carbon monoxide, which runs the engine. So I don't need gasoline to run this. My log splitter, I run it on charcoal. Behind it is the wood for my house heating, but the charcoal gas runs my log splitter. I no longer use gasoline. And then this is my farm oil cub with a charcoal gasifier on the front. And behind it is a electric generator with a charcoal gasifier mounted on top of it. So, charcoal. It's a homemade fuel. We can use it to reduce our reliance on fossil fuels. It's an investment in your soil. It can retain nutrients, increase soil health, retain water. It can be sequestered carbon. It literally uses carbon dioxide from the atmosphere, puts it into a form that doesn't decompose. Finally, it can be used as a filter to remove nutrients from the air and the water to reduce pollution. So all green plants produce material that we can grow and make into charcoal. So with all these benefits that we get from charcoal, I think it's time to start to ramp up and start using this amazing product. As we enter the more modern 21st century, this ancient material can really help us mitigate some of the problems we'll be facing. And with that, I'm going to, one other thing I'd like to mention. There's a lot of information available in the Biochar journal. It's actually a new journal that got published here, started 2 months ago. And a lot of the information available and research is available in that journal. If you just Google it, Biochar journal, tremendous wealth of information on charcoal in the soil. So with that, I'm going to end. Sarah, I'm going to throw it back to you.
Thank you so much, Gary. That was a great overview, and it's so great to have a lot of pictures like that to really get a good idea of what's going on. I know it's 2 o'clock at this point, but if any of you want to stick around for the questions, I'd like to go through a few of them. So if any of you have an extra 10 minutes or so and want to bear with us, we'll try to address at least a few of these questions that have come up. I guess we'll launch into that now, if that's okay with our speakers in terms of their schedules.
That's fine with me. Thanks, Sarah.
Okay, great. So I'm going to start with a few questions that popped up at the beginning that are just clarification questions for David. A couple of them address application rates. What is the range of application rates? Is it to 60 tons an acre, as you had suggested in one slide? Another participant had asked about the rate of application per acre or hectare, the Australian example that you used.
We generally use about 10 tons per acre. 5, if you don't put 5 on, it's hard to see any measurable effects. 50 tons per acre was too much. We've actually seen some detrimental effects at 50 tons per acre. So I think in the 5 to 10 ton per acre range is probably the best. In the Australian example, the rates ranged, these were measured in tons per hectare, but they ranged from 0 to 100 tons per hectare. So they had quite a variation there. They did not see a yield response until they got to above 20 tons per hectare in that example.
Would you say it's a kind of a wait-and-see approach to find the optimal application per site, or are there some general guidelines in terms of what currently exists in terms of soil characteristics that would lead you to apply a certain rate?
Well, my approach to this is always to ask what is the problem you're trying to fix. If it's nutrient and water holding capacity, is it a soil physical problem? Are there other problems that you're trying to address? And then to design a system, fixes that specific problem. So if you've got a hard-setting E horizon, it won't do a lot of good to put the char on the surface of the soil. You're going to have to figure out some way of getting the char injected down into that horizon and figure out the appropriate amount of char to achieve the mitigation that you're going to need. In terms of nutrient and water holding capacity, generally we are applying the char in the surface of the soil. If you have a horticultural application or a backyard garden, where cost is not the major concern, and you could consider higher rates of char application. Obviously, pre-mixing the char with manure is a real valuable. Composting it are real valuable for those kinds of applications. So again, you need to mix the char and the science and the knowledge together to develop unique applications and unique solutions.
Thanks. Question with that in mind, what you said in mind about the need to understand the variability in terms of what the goals are of using this. How long would you have to wait to see the positive effects on soil properties appear, and how long would those last before reapplication or just into perpetuity?
Sure, that's a very good question. We've seen the response the very next year. So if we put the char on in the fall, we've seen it the following growing season. I would be a little hesitant to put the char on early in the spring and expect to see a response immediately. It does take some time for the char to equilibrate with the soil. If, on the other hand, it's been composted with organic matter or manure, then you should see the response right away. So, again, it depends on how you set the system up. And what was the other question, Sarah?
About how long would those beneficial characteristics last before either you need a reapplication or before you see the effects start to drop off?
Sure. The truth is we don't really know. The half-life of carbon in char and soils is certainly measured in, somewhere between tens and thousands or even tens of thousands of years. Some low-temperature chars may degrade fairly rapidly. Most chars that are produced at around 500 C or higher will be stable for hundreds or thousands of years. So one would presume that the beneficial effects would last as long as the char is present in the soil. But we haven't waited around long enough to find the answer to that yet.
Thanks. There's a question about that techno-economic analysis graph that you had posted. You listed a lot of vegetable and conventional crops, even some silvicultural applications. Any guesses on where bioenergy crops for dedicated energy crops would fall on the techno-economic analysis graph?
Well, the previous slide showed an economic analysis in the example of harvesting corn stover for a bioenergy application. Let's see, keep going. Right there. Oop, you went past it. No, okay, yeah, there. Okay, and in this example, estimated that the char could be worth around $250 to $300 a ton in a cornfield. Now, if you put it in a dedicated bioenergy situation, such as miscanthus or switchgrass, there are other issues there. How do you get it incorporated? You almost have to apply it before you seed the perennial crop, or else you have to apply very small amounts every year and let it gradually work in through bioturbidation. The value for a dedicated bioenergy crop, again, I'm going to say it's probably be a little bit less than in a cornfield, because perennials provide some of the soil quality benefits that you don't have in an annual crop like corn. They've got a rooting mass, a large rooting biomass, and they're protecting the soil from erosion and so on. So I would guess it's probably going to be a little bit less than the 250 to 300 that we see in a cornfield.
Makes sense. The next question, I guess both of you might have some input on. This participant asks two questions. One, the difference between biochar and charcoal, and two, why aren't growers using charcoal already? If the yields are good and if these benefits have been well demonstrated, and if it's widely available, is there a need to wait for an established bio-oil market to use this as a byproduct?
Well, I'll start, and Gary, if you want to add afterwards, go for it. My first response is that the biochar industry is minuscule. It's a niche market at this time, very low volume of production, and very high price, $2,500 a ton kind of range, which is cost prohibitive for any commercial application other than extremely high value horticultural markets or environmental markets that where cost is not the limiting factor. That's the whole purpose of the techno-economic analysis, is to see what these different industries could potentially afford to pay for biochar, and roughly the size that these industries might be able to use. So I think it's going to be the industry has to develop, the char has to be available, and before we're going to see these kinds of applications taking off. Gary, did you want to add a few comments?
Yeah, I'll jump in here. Traditionally, we do not need to use biochar. We just go use fossil fuel derived nitrates or ammonia, and then we put it on the ground. The effects are almost instantaneous. We get a big crop of that year because we give them the nitrogen, the phosphorus, and such, and then we just repeat the same thing next year. We don't have to use biochar because we have access to all this fertilizer that we can just mine and apply. Biochar is not a fertilizer. It is a soil amendment that holds nutrients in the soil, keep them in the soil. So the benefits of putting it on are long-term. And biochar is really an investment to the soil over literally over the centuries. So it's not a quick fix. It's expensive. It's not in our tradition, and we have not needed it. As the price of mined resources used to develop crops increases, as the use of herbicides and anything fossil fuel derived ultimately is not sustainable and it will fade away, we need to transition to a more sustainable system, and biochar can do that, but it's not fast, it's not real sexy, and it's not our tradition. But I see that as our future. We're going to have to do that. Okay, that's in a nutshell.
Thanks, Gary. I think that addresses a couple of other questions that popped up too about just the general nature of biochar's performance in the soil. There's another question about the original feedstock that's being used to create biochar, which is later used on the landscape. So certainly I think in Gary's operation, wood is really the primary feedstock of interest, but in a distributed pyrolysis work, one could imagine the use of field residues, stover, or dedicated crops like switchgrass, shrub willow, so a variety of wood and grass-based biomass being used. Are there significant differences in the performance or in the quality or characteristics of biochar that originates from wood versus various other field crop biomass?
Yeah, I'll jump in here. There are biochar quality is very important. The type of feedstock and the thermochemical processing conditions both influence the quality of the char product that you get out. Hardwoods and softwoods tend to have relatively low ash content, whereas herbaceous biomass, grasses, corn stover, tend to have higher ash content. The ash content is related to the liming ability or the ability to neutralize acidity in the char. If you use a manure, you can have very, very high ash content, very high nutrient content in a manure biochar. So those properties are very important. The temperature of the pyrolysis is also important. High temperature biochars may contain aromatic hydrocarbons, including naphthalene and other potentially even toxic and carcinogenic compounds. These have been associated so far with high temperature gasification chars, and so one needs to be very careful not to use a char from those kinds of conditions. Also, if your feedstock is contaminated with heavy metals, for example, pyrolyzing green tree timbers that have been treated with copper, that copper will be concentrated in the char and can again be phytotoxic, poisoning plants. So it's very important to look at char quality. In addition to the presence of toxic compounds and ash, another consideration in char quality are the physical size of the individual particles. Is it a dust? Is it a chunk? The density of those materials. Some of the nut chars tend to be a very high density material with a relatively low porosity. Some of the hardwoods and softwood chars have lots of internal porosity. Some of the herbaceous chars tend to be more fragments of material. They don't hold as well. They're not physically as strong as chars coming from woody biomass. And again, that's a problem. It's also an opportunity, because I say it's a problem because it means that char quality varies a lot. There's not one char. There are many different types of char. It's an opportunity because you can select the right char for the right application and take advantage of those differences in properties as long as you can put the right char on the application. Gary, do you want to add something to that?
I will make char out of anything. Grasses, corn. Boy, when I was bales of corn stover, I thought, man, char them, energy out, but then turn the rest into charcoal and put it back into that nice black soil that was all around those bales of corn stover. I'm not as particular about I use a low-tech method, so I don't have a lot of control over the heat. And the only thing I would absolutely agree with as far as char specifics is do not use any treated lumber or any materials that have paint on them. Those are not suitable to be made into char and then put on your ground. Whether it has high ash content or low ash content, to me that really does not make any difference, and I don't have any quantitative information on that. But if there's high ash, fine. I mean, I'm putting ash from my wood stove out onto the fields also, so I'm actually adding that, supplementing the biochar with the ash from my wood burners. So I don't mind ash, but we do have high or low soil pH, so it actually helps lime it and adds the calcium and phosphorus back in. Definitely do not use
Gary,
wood.
Gary, my comment about the pH and the ash is, if you have out west, there are a lot of calcareous soils, and putting a highly alkaline char on a calcareous soil might be problematic. Putting the same char on an acidic soil could be beneficial. So it's important to mix both the soil science and the char chemistry to get the right combination.
Yes. Yes.
Thanks. That was a very thorough answer to that very good question. So I realize we've gone on quite a bit longer than we usually do here. There are so many excellent questions, and wow, a lot of information in a 1 hour presentation here. So I think unfortunately we might have to call it a day there, but I'm sure that our speakers would be happy to address additional questions via email or via their other professional platforms, and you can also, pose your questions through the New Bio project, and we'll do our best to get back to you on those. You can also consult some of those resources that Gary had mentioned, or have a look at some of David's research. Are there any final thoughts that you have?
I'll just say I think.
I'll just end with thank you for the participants.
Yeah. I want to say thanks for the opportunity to be here, and enjoyed the afternoon. I think char has a potential for great future. I think it's also a challenge, and it's important to do the good science and technology that using it in an appropriate way. And obviously, safety comes first. It's a combustible material. And there's an inhalation hazard if there's a high dust level. So a little water goes a long way at reducing both fire and problems. After that, thank you much.
Thanks very much. That's a good reminder. Thank you all for joining us. We hope to see you at future webinars.